Good morning, and thank you for coming this early. My name is Andrey Breslav, and I'm today telling you another bit on Kotlin. That's a good tradition. I'm telling something on Kotlin every year. For those of you who haven't been here one of the last 2 years, Kotlin is a programming language. We developed at JetBrains. It's compiled to JVM bytecodes and JavaScript. And today, I'm telling you about something new we're getting this year. It's reflection. It's in the works. So I'll appreciate all the feedback very much. OK, so actually, it's not only reflection I will talk about. It's introspection in the broader sense. And introspection, according to a smart book, is examination of one's own conscious thoughts and feelings. So as soon as your program examines its own thoughts and feelings, it's doing introspection, and that's what we are after. My legal slide. And so again, it's work in progress. Most of what I'm showing today is not working fully yet. Some of it is not even been started in the works. But please do judge strictly, because we need the feedback. If you catch some design flow now, it will be a lot better than if we catch it later in production. So I'll be talking about a reflection API and some goodies on top of it. And we'll start with the conventional things. So why do people want reflection? They actually do want reflection very much. And it's like the third question people ask about Kotlin. When somebody starts using Kotlin, the first question is probably how do I install it? The second is, why do I have types on the right? And the third is, how do I use reflection? And the answer right now for the beta we have for the users is you use Java reflection. So everything is, of course, compiled to Java classes, and you just resort to what you're used to in Java. And what people want to do with it is many, many magic things, like dependency injection when you want to wire things together, like data binding when you want to present something to the user and get it updated properly, and generally convention over configuration. So what people use it for is introspect the structure of your program and shape something after the structure. So if I have classes with methods here, I want something with something inside there that's structured pretty much the same way. And of course, there is another very important set of use cases, which are hacks, workarounds, and black magic of all sorts. Because if you can't do it the right way, you use unsafe or reflection, and that's important as well. OK, so what do we have in a conventional reflection API? We can ask an instance what your class is, and it will tell us, give us an object, right? And then we can query that object and ask about members, about fields, methods, ask about supertypes, annotations, and ask it to instantiate if it's not abstract. Then for methods and fields, we can invoke them, of course. And for expressions, we can do anything in Java. But we may, if we are more Lispy, do something even with expressions. And I'll get to that a little later. Do you have any questions at this point? Probably not. Everybody knows what reflection is. All right, so first question is, why anybody wants anything but JAVA.LANG.REFLECT? That's a great library, used for ages. Everybody knows how to use it. Why have some specific reflection for Kotlin? Why not reuse Java reflection? The answer is we have too many things that do not map one-to-one to Java. An extract from this list is here. It's top-level function that in Kotlin doesn't belong to any class. So of course, physically in bytecode, it belongs to some class, but that class is not a class from the Kotlin point of view. Then some functions have default arguments, and they're encoded somehow. So to call such a function through reflection is a pain. Then there are properties that group together a field and one or two accessors. There are all weird kinds of types, like nullable types, and some imaginable types like nothing that has no counterpart on the JVM side. Mutable collections, we distinguish between mutable and read-only interfaces for collections, but compile them down to JDK ones. So again, on the reflection level, there is no way to distinguish between a mutable list and read-only list, so on and so forth. One other thing is modules. In Java reflection, you do not introspect a package. So what you have for a package is its qualified name, and that's it. But having a notion of modules in the language, you could probably introspect the module and ask what packages do you have and what classes are in those packages in this module. So these are the reasons why we want our own reflection. And this is where interesting things start. So to implement reflection for Kotlin, we need to, at runtime, to provide the user with basically the symbols that compiler constructs for Kotlin declarations so that the user can introspect them somehow. And what compiler is doing here is it's reading the source, creating symbols, and as well, while reading the source, it reads some kind of libraries that come in the form of jar files, and somehow extracts Kotlin symbols from there as well, processes them, and spits out another library, another binary with Kotlin symbols as well as Java symbols. So Java symbols are for the runtime, and Kotlin symbols are for us, for later use by the compiler or by reflection. So to store this information here in jar files, to be used by the compiler and by reflection, we have to somehow embed it into the class file format. And there are two possible options: either use custom class file attributes or annotations. So attributes are mostly out of the questions. Other people try that, other people being Scala, and they switch to annotations mostly because tools do not respect custom attributes very well, and they tend to strip them out too often. With annotations, there are two options, and these two we tried, and yeah, went after Scala after all. So with annotations, you may want to annotate each individual method or even individual parameter there to add your bits of information that are missing from the Java meta information. And this way you get it more granular, or you could put one huge annotation on the class file, putting all the metadata for this class file into this one single annotation, and forget about reading everything else. So we started with many little annotations. It turned out to be inconvenient, so we switched to one big annotation. It's easier to manage and takes less space, so on and so forth. So this one big annotation will be the source of Kotlin symbols, both for the compiler and the reflection. So the class file looks like this. So this part is for Java. It's normal vanilla Java definitions. And this one is for us, some kind of annotation Kotlin class that in a string, really, it encodes a huge amount of binary data. Hopefully not so huge. So what the compiler does, it takes classes and Kotlin sources. From sources, it extracts the AST and transforms it to symbols. From classes, it takes the annotation and transforms that to symbols as well. So at runtime, we have to do something similar. Again, take the annotation, transform it to symbols, but the source for the annotation won't be a class file, will be actually a JAVA.LANG class object from Java reflection. So what we have to do is to cut this part that transforms the annotation to symbols from the compiler and ship it to runtime for the users, which is a technical challenge, huge refactoring that separates this process from everything else. It's done. But it was a challenge. OK, so far so good. We know how to get all the symbols from a runtime object, a Java.LANG class, and present it to the users in the form of symbols. There is a bunch of nasty things in there. One big issue being annotations. I don't mean the annotation that holds the metadata, but the annotations that you, the user, put manually on your functions in Kotlin. At runtime, they're presented as JAVA.LANG annotation because we want compatibility. But at compile time, they are obviously not instances of some weird interfaces. They are some kind of internal structures of the compiler. And these two interfaces do not unify. So we have to somehow figure out a way to, for wrapping this so that the same API can be used in the compiler and at runtime, but you can still have access to your annotations in the Java sense. That's the technicality, but there will be those nasty technicalities popping up all over the place. So the question number 2 will be, OK, I'm good with my Kotlin classes. So whenever I see this annotation on a Kotlin class, I can load my data from there. That's all right. But now my user comes to me and says, OK, I have a Java.LANG string. I mean, I have a string in Kotlin, which is at runtime, of course, a Java.LANG string. And I want to introspect it with uniform reflection. I don't care what class that is. I wrote something against Kotlin Reflection API, but I want to pass the string class into it. What do? OK, you go through the same mechanism, but Kotlin never compiled the JAVA.LANG string class. So nobody put this annotation there. And we have to somehow reconstruct the symbols without having our data stored there by the compiler. So yeah, the picture is like this. There is no annotation there. Of course, the compiler itself solves the same problem, because when it loads something from the JDK, when using Java libraries, pure Java libraries, it's not limited to Kotlin libraries, it somehow reconstructs from the Java declarations Kotlin symbols and uses them as well as Kotlin native symbols. So there is some kind of Java to Kotlin conversion on the declaration level, and in the compiler we use it from Java sources and from Java classes, and now we have to add another source of information, Java reflection, to apply this transformation and actually get the symbols. So this is a little challenge of unifying our internal API for introspecting Java code with a lot less rich API of reflection, but we're working on it, and I believe we'll do it. Now, nasty things start popping up here. As usual, if you do anything with Java and you're not Java, there are little glitches all over the place. So our biggest glitch all the time is nullable types. Like whatever compatibility thing you're thinking of, think nullable types, they will be a pain. But we still believe it's worth it. So in Java, you may or may not provide some kind of documentation on whether your method returns null or not. Right? So somebody was so kind to document this method, to annotate it with not null, and tell us that it never returns null. But for a middle name, he didn't. And in this case, it's relevant, but it might be not, because some people are just not kind at all. They don't put any annotations on their Java classes. So in Kotlin, something annotated as not null will be normal string, and something not annotated anyhow will be a string with a question mark, which means that it's nullable, and you cannot simply call a method on that. Before you call a method, you have to check whether it's null or not. And if you have a huge Java library with many, many methods, and you're trying to use it in Kotlin, it turns out that if you don't have those annotations, it's a pain, because you have to check things for nulls a lot more than you'd like to, because many of them are not null, but that's written only in the Java doc, and Kotlin compiler is too stupid to read that. So what we do at compile time to mitigate this is we use some external annotation facility. So actually, we generate those by inspecting your bytecode, and I'll tell you about that in the workshop today. But that's not the point. Somehow, the user got this annotation file that tells that, OK, if this method in this class doesn't return null, that expects a not null value, so on and so forth. And actually, the transformation, this Java to Kotlin symbol transformation, it not only takes the whatever bytecode or source, but also takes the annotations. And from these two sources of information, it provides the symbols with the right typing. Now, can we have those annotations at runtime to facilitate reflection? Well, probably yes. But again, if we're talking about reconstructing the symbols for, say, JDK, I never compiled JDK myself, so I cannot ship this inside the RT jar. Right? So I have to put it somewhere else. And the only place I can put it in would be my jar that I'm emitting from those symbols. And this means that if I compiled like 20 libraries against JDK, each of them ships the annotations, and these are not small. So there is actually no practical way of shipping all the extra meta information for all the Java code you do not own yourself, for it to be on the class path and be introspectable. So we currently perceive it as a necessary evil that we cannot reconstruct absolutely identically the types that the compiler would reconstruct. And at runtime, you'd have a lot more nullable things in your reflection types than you'd have in the compile time. Go ahead.
When I have the compiler extract just the annotations that you need and throw away the rest of them when you're building your jar. So embed in your generated jar the annotations
Yes, that may be a middle ground, but we're talking about reflection, so we never know what classes they will introspect. So if it would be only introspecting the code we're actually calling statically, we'll be fine, but we don't know what will be introspected. All right, any more questions? Yeah.
What was the rationale behind kind of deciding that everything that doesn't have the null annotation is basically kind of unsafe? Why didn't you do something like row types? I mean, some first state in which you don't
Yeah, I see.
know.
So the question is, why bother with this, making this strictly nullable? Why not make it something ambivalent, like which allows a call, but you know that it's unsafe? Well, it's an option. We're still struggling for having something really safe in Kotlin, the safe type system. But if we struggle that much a little longer, we'll probably introduce a new thing. OK. So the first part of my talk is over. We're talking, just a second, we're talking about the reflection APIs. They are pretty much similar to Java's. We have some kind of technical solutions for metadata representation, and we have some problems, but they're probably mitigatable.
Did you consider inferring this, like basically doing the analysis of bytecode at runtime with, I don't know, JAVA.LANG or something like that? So basically recreating those annotations when users ask.
Yeah, the question is, can you reconstruct the annotations at runtime by inspecting the bytecode you're running? Well, first of all, I'm not exactly sure whether you can actually load bytecode for any class at runtime. You probably can most of the time. But anyway, the reconstruction of annotations would be really expensive, time-wise, because we have this inference tool, and it's not an online tool by any means, because it's, you know, it's a fixed point computations over a huge code base. It's no way we can do that. OK, let's go on. Now let's talk about entry points, how you enter reflection. So in Java, there are two most widely used ways. It's class literal, like class name.class, or an object.getClass method that gives you the runtime class for that instance. And here are, so my syntax is tentative here. It's not fixed yet, but anyway, well, stick to this. So these are the two familiar entry points. When you have a class, :class, it's the class literal. And expression : class is the analog of calling getClass. So that's easy. Now, something that looks similar to what Java 8 has is statically resolving a member of a type. But the difference with Java 8 is that we want this to be a reflection object, something you could not only call, but also ask what's your name, who's your owner, so on and so forth. This is something we're probably going to have in Java sometime later. Yeah, so this is a pretty obvious use case. You have to somehow figure out the generics, and I'll get to that later. And the same for packages, because we have top-level functions, and the same for expressions when you want something bound to the receiver. And that's a slippery point for Kotlin, because there may be effectively two receivers, and so on and so forth, but it's too long to explain, and I'll skip it here. Another thing we're thinking about is expression : type, which is getting a precise type with generic arguments. But Kotlin does not reify generics, so we'd have to play some kind of collaboration between compile time and runtime, and it won't be complete. But we are thinking of the use cases for this, and maybe we'll have it because it's good enough even this way.
So just to be clear, the : class and : type is literally what you write, but : member is a meta variable. You do, you know, org sample bar : :
Oh yes, yeah. Thanks. Yeah. So this here is a keyword, and this here is a keyword as well, and this is a keyword. But these are actually supposed to be names, some particular names. Yeah. Yeah. Thank you.
What about overload?
Overloading. Yeah. So if this member here is overloaded, you're supposed to provide the disambiguation in parentheses, just passing the types in. And type inference tries to be smart, and if this disambiguation can be drawn from the context, you don't have to do it. OK, so use cases for different syntactic forms. So the most common use case is what Java 8 covers as well, is just passing something as a value, some method or some property reference as a value to a higher order function, because a lambda form for it will be too verbose. So I could do something like this in a lambda. It's valid, is easy because it doesn't have arguments. But if you have to wrap a 3 argument method into a lambda, you have to duplicate the list of arguments. Not no, you have to spell them out, but you have to spell them out twice, because you have to declare the parameters of a lambda and then pass them as arguments to the method. So you really need the literals here. Next thing that's close, but it's just an interesting use case that pops out a lot, and we like it very much, is using constructors as values. So in Java, it's a common pattern to pass a class value around, because it carries on the type in the generics. So that's something like this that wants to instantiate and then return the correct type somewhere. It will use in Java a class object and call new instance there and so on and so forth. But in Kotlin, you can stick with a factory function here. And as a factory function, you can pass a constructor in because it carries the information. So this div is actually shorthand for whatever package :div. And since we don't have a new operator, a constructor in Kotlin looks like a top-level function. So this is just a reference to the constructor. And when you pass a constructor in place of your factory function, that's all you need. So this is very clear syntax on the client side. You're basically kind of passing the class in, but you don't have to be limited to classes. You can use any factory function. And the client is usually passing constructors, so it's pretty clear what's going on there. Any questions here?
The second parameter is your lambda.
Yes, this pair of curly braces is this lambda. OK. Another use case, which is very important, is data binding. This is something where C# is way ahead of Java, because they have a not very clean but working way of introspecting properties. And we don't even have properties in Java, right? So data binding is the use case when you have some kind of a user interface, some kind of a model, and you want to bind a property in the model to a control on the screen, so that when you modify the control, the data gets propagated back to the model, and when you modify the model, it's updated on the screen. So that's why it's very important to have literals for properties. And we even combine it with something called delegated properties, and if I have enough time, I'll tell you about those. So that's what a bind would look like in a binding framework when we get reflection for Kotlin. You just say, OK, for this text field, I want to bind this property, and that's it. Any questions here? Should be obvious. Now, questions start. So the question is, you have literals, great. What about generics? So for a normal function, it's pretty straightforward. If you have a foo that takes a string and returns foo, your : foo, which is a literal for that function, is a function from string to foo, and that's it. So what do you have for a generic function that has a t and then takes a t and returns a t, for example? So the correct type for this would be for any t from t to t. And this is a quantified type. We don't have those in Kotlin. And this is something that leads to a rank to polymorphism, which Haskell has, and even Scala doesn't. So we probably don't want that. And people actually ask me rather regularly why when we have rank 2 polymorphism, because it's considered to be like a theoretical problem in type theory, because they want complete type inference. And this is what makes it undecidable, but we don't care because we don't have complete type inference. So why not? The actual answer is that it's all hidden in the encoding of how function types are encoded into classes, because we actually have a uniform type system. Everything is a class, probably generic. And so we encode the function types as normal instantiated types. So when you say from foo to bar, it's actually function 1 from foo to bar. And there are classes function 0, function 1 through function 22. When at 42, ask Martin Adersky. I don't know. We just copied the number from them. So this is the straightforward encoding because you know, all the information is here, you know how it works. But now you bring generics in. So imagine we have this kind of generic function type. So for all t's from list of t to t. Now how do I encode it as a instantiated type on classes? I could say generic function from list of t to t, but then what's my t here? It should be defined somewhere outside this type. Doesn't work. Now, okay, what about this? This is nonsense anyway, because this t is not a declaration, right? It's just another use of t. So something that could probably work, and this is something you can do in Scala, would be to say, okay, here's my generic function of one value argument and one type argument, so which already makes it an explosion, right? We have to multiply 22 by 22 for all the parameters for 2 dimensions. But even there, I have my parameter type and the return type, and these have to be modulo the actual type I'm passing in there, right? Because this is supposed to be a list of t, and this is supposed to be a t. So when I pass an actual value for t, these are supposed to be a list of string and string, for example. So here, I have to have my type parameters taking arguments, type arguments to produce actual types. So I have to express something like a type constructor in the language to pass it around. That's called kinds, and it's tricky, and forget about it. Yeah, so this is why we don't have rank 2 polymorphism, because we just don't have a way to cleanly encode it in the simple type system we have now. So for generics, we do pretty much what everybody else does. When you have a generic function in maybe generic class, you can specify type arguments for both. So you can pass t prime for foo, and then r prime for bar, and then you get the instantiated signature for the function. Otherwise, it just has no type, and you can't use it. Any questions here?
But you can relate the type variable r to the type variable t, right? You can say that r extends t.
You can, yes. Yes, and this will be just checked at instantiation type, times. OK, how am I doing? Oh.
There was that paper mixed site variance.
Yes.
Is that incorporated or something you think about or something you said now?
It's, I would say it's a cleanup of what we have now. So it's not fully incorporated yet, but the ideas from it are in the language. Yeah, so it's somebody who really knows what he's talking about came and looked at what we have and said, OK, if you clean it here and there, it will be good. OK, so do I have enough time? We'll probably do. Another thing is, that's an open question. We don't know whether we are going to do this or not. It's taking a type of an expression as a reflection value. So a class for something that is actually a list of integers is obviously whatever implementation class you have there. But if you want a type of x, which is declared as any, the compiler can give, the runtime can give you no better than just an array list of whatever type I don't know. Because there is no way to reconstruct this because we erase generics, right? But oftentimes it will be that the actual static type for x will be a generic type, list of int. And when you statically know that it's a list of int, and at runtime you know that it's an array list of something, it's very easy to deduce that it's actually an array list of int. So we could reconstruct that at runtime. It wouldn't be complete, so sometimes we wouldn't be able to. But oftentimes we would, and maybe it's so valuable for the users that we should. So that's why we're looking into use cases now.
But what about subtyping? There can be any subtype of list of int, right?
You mean it can be an array list of whatever subtype of int?
Yeah.
Yes. Yeah, this is another another imprecision here. Correct. What's that?
Technical term and soundness.
Imprecision is sort of a war word.
Yeah. Yeah, that's why we're not sure about having this or not. Another thing that's not strictly related to to reflection but has some implications is something we call delegated properties. When you can say that whatever property I have, it's not simply a pair of get and set on some kind of stored value, but its get and set are implemented by some object here. So for example, I could have a class called lazy that basically implements a lazy computation, and here's a get method. So anything that has a get method of write signature can be a delegate for a property here, and thus my property becomes lazy just because the implementation works this way. So this is some kind of mechanism we can give to the user so that they customize behavior of their properties. It can make properties observable, lazy, thread safe, so on and so forth. And these delegates are very interesting for those who try to introspect properties, of course. So there are two ways in which we could provide this to them, and we're not sure which one is better. So one way would be to say that I have a static, a keyword basically, that lets me statically access delegates of properties of known types. So if I know that this property has a delegate, I can give the delegate to the user, and so my foos alone is just property of list of foo, and its delegate is lazy foo, which we can see here. Another option would be to encode the delegate type into the property type itself. So it's delegated property whose own type is list of foo, and the implementation the delegate type is lazy of foo, and then we can pass them around in a type-safe way, and the user can introspect that on a more generic basis. So the trade-off here is this is a simpler type, and this is a more powerful construct. So we're not exactly sure, but there are options there. OK, any more questions? Criticism? Yeah?
How do you encode type-safe lazy?
Type-safe lazy? What is it? What's safe about it?
By lazy and by type-safe, or thread-safe, sorry.
OK, thread-safe. All right. So you can't have more than one delegate. So there are different classes that implement lazy in different ways, like synchronized lazy, volatile lazy, so on and so forth.
But you have to implement all the...
Yeah, all the three that are there we did implement. Yeah.
Are you concerned about exposing the delegate information because does that break encapsulation? Like, am I going to
Yes.
later and change that class, but now I broke all the injection code because it assumed it was delegate and now it's not, but the
Yeah.
user can't tell the difference in normal code.
Yeah, we'll actually have the access modifier on the delegate. So you decide whether you expose it or not. OK. So next thing is code introspection, something that Lisp has and nobody else does, or almost nobody else does. So let's start from use cases. And first use case comes from C#, where they have this awesome thing called LINQ, which is you can have an expression in the language that uses some language constructs in lambdas, but at runtime those constants are actually available not as executable bytecodes, but as code trees. And the runtime transforms these trees into something that database server understands very well and can execute efficiently. So this actually gets transformed into a query, single query to the database, not to a number of calls to some kind of an API. So it would be very nice to be able to inspect this code here to transform it to some kind of an efficient form for data access.
So just to be clear, that's not LINQ.
This is not LINQ. This is this is not C#'s LINQ. These are calls that look like C# LINQ in Kotlin. And LINQ has also this SQL-like syntax, which is not essential, because you can write all that in lambdas and it will work the same way. So this is one use case. Another use case is related to the web. And we are very fond of this ability to express many web-related things. And Kotlin is a single language for markup, for styling, for templating. And Kotlin compiles to JavaScript, so you could actually do the whole HTML page in Kotlin without resorting to any other languages. But the problem here is that some parts of the code that represent the HTML file, so this basically generates the HTML. So these are function calls that simply create tags, but this this here is an event handler whose body is supposed to be in JavaScript. And so I'm supposed to compile this file so that most of it works on the server and thus is translated to Java bytecodes, but this small bit in here is supposed to work on the client and be translated to JavaScript. So how do I tell the compiler that, okay, this tiny bit here gets transformed to JavaScript? There are a number of approaches here, maybe compiler plugins, maybe macros, maybe something else. Another approach would not to tell the compiler anything about translating this part to any particular language, but just ask the compiler to reify it as an expression tree, and at runtime, let the framework that actually provides all the functions here just call the compiler as a service to translate it to JavaScript. So that's another use case for expression trees for code introspection. And this is basically what C# does. We're going to do pretty much the same thing. So the idea there is that if the expected type of your piece of code is expression of whatever type it is, the compiler knows that it shouldn't actually compile this expression to bytecodes, but should emit the factory calls that create a tree and pass the tree to the consumer. And then the consumer will translate it and so on and so forth. Questions here? OK. That's it. So the introspection facilities we're going to have for Kotlin are normal reflection APIs, type-safe reflection literals that enable access to known things as reflection objects, and expression trees to introspect code to leverage the use cases I presented. Do you have any questions?